Hello everyone, my name is Jaycent Ongris, and I am representing our research team, which consists of myself, Eduardus Tjitrahardja, Dr. Fariz Darari, as well as Dr. Fajar Ekaputra. We are going to present our work on towards an open NLI large language model based system for knowledge graphs. Case study of Wikidata. To start our presentation, we would like to acknowledge that these research were supported by the Wikidata Research Grant 2024 from Wikimedia Indonesia, whose funding and commitment to open knowledge made this study possible. Let's start talking about large language models' limitations. It is commonly known that large language models have revolutionized the information retrieval due to its outstanding natural language understanding capabilities. But several issues persist, such as hallucinations, lack of interpretability, and the last one is the difficulty in expanding or revising the embedded knowledge. To mitigate this condition, Retrieval Augmented Generation, or RAG, was introduced by combining large language model with non-parametric model, or retrieval-based, to store knowledge. The next thing we would like to introduce is the knowledge graph. Knowledge graph is a data structure to represent knowledge in the form of a graph, which consists of two main elements: entities, which correspond to nodes in the graph, and the second one is relationships, which correspond to edges in the graph. One of the most prominent data models used for the knowledge graph is called the Resource Description Framework, or it is often abbreviated as the RDF. The RDF data can be queried using Sparkle, just like SQL, but this is for the RDF data. If we were to represent the knowledge graph in this right side of the screen using RDF format, it will be in the set of triples, where each triple consists of subject, predicate, and object. For example, dogs is a subject, is a predicate, and animals is an object. So there are 1, 2, 3, 4, 5, and 6 triples in this knowledge graph. A concrete example of the knowledge graph is Wikidata. Wikidata is an open and collaborative knowledge base launched by the Wikimedia Foundation, and the structure of data stored in Wikidata is composed of items, properties, and values which are connected in statements that resemble RDF triples. And this data can be retrieved through Sparkle queries, which they also actually provide through the Wikidata Query Service, or WDQS. This is a page of Indonesia in the Wikidata. As you can see, this is called the properties here, and this is the objects. Meanwhile, this is the subject, Indonesia. Additionally, the data can be exported into RDF format as well. Next, we will look back into the RAG system, but in this case, we will try to incorporate knowledge graph in the RAG, which is commonly known as the graph RAG. There are several advantages of graph RAG instead of over knife RAG system. The first one is to enable contextualization of entities within the graph through their relations. The second one is to facilitate the use of graph theory algorithms like community detection or centrality analysis to give a more detailed insight on the graph. And the last one is to provide more transparent and interpretable reasoning through graph box tracing. In this work, we construct a natural language interface for question answering over Wikidata knowledge graph using the graph RAG paradigm. And in constructing the NLI, we aim to use only open source components within the system to enhance the transparency and to facilitate specific customization based on users' specification. This is the pipeline of our system. It might seem complicated, but we will delve into each section specifically. It starts from this side, where the entities from the question are extracted, and it ends in this stage where the obtained Sparkle query execution result is converted into natural language. The first one is the entity extraction. So given the user's question, the large language model will extract the relevant entities that exist within the question. You can see here that humans born in Indonesia, it will be extracted the entities to be like in human and Indonesia. This is the extracted entities from the first stage. The next one is for every extracted entity, the keyword is used to retrieve the top 5 related Wikidata entities using Wikidata API, as you can see. And the retrieved data includes the URI or the ID, the label, and the description of the entity. Upon obtaining the top 5 entities that matches the extracted entities, we can ask the LLM to determine the most suitable entity from the list of the entities retrieved before, based on the context of the user's question as well as the description for each entity. And this is the result. The next one is the large language model will generate the most appropriate Sparkle query to answer the user's question based on the determined entities before in this section and the predefined properties of Wikidata that we augment in the prompt, which we will tune later to see how does it actually can affect the performance. And the last one is to generate the generated Sparkle query will be executed against the Wikidata endpoint, and the result will be passed as the context for large language model to generate a relevant response to answer the user's question. Regarding dataset, we handcrafted our dataset because we have several restrictions. So the dataset we created in order to ensure that the query only contains properties within the predefined properties list. And our dataset is composed of 31 rows across 3 main domains, the animal, artist, and written work. And to evaluate the result, we use Jacquard similarity. And we focus to evaluate the result of the Sparkle query execution as it provides a more structured output and it is very easy to compare compared to using free text and large language model or the large language model generated answers. Use Python with the following libraries in developing this system. And for the LLM, as you might have noticed before, we use the Mistral 7B instruct. This is based on the Mistral 7B models, foundation model, which has been fine-tuned on the instruction dataset. We use 3 prompting strategies. The first one is the few shot prompting, where we give several examples, the 0 shot with no example, and the last one is the chain of thought prompting, which is incorporated in the second to last steps to generate Sparkle queries to improve the reasoning ability. And the prompt is generally organized in 3 sections: instructions, context, and examples. However, this is not quite strictly followed because there are some additional sections that needed to add some other sections, such as the question for the last stage of the pipeline. The user interface, you can see this in your screen, and the evaluation. So in this evaluation, we modify the mentioned properties in the prompt to see how does it actually can affect the overall performance of the system by inspecting the average Jacquard similarity score. And as you can see here that the model performs very well on the top 100 and given the Wikidata query service examples properties. Perhaps it is quite straightforward that the top 100 properties are the most frequently used properties in Wikidata. However, for the WD key as examples, as you can actually take a look at the website of the Wikidata query services. They provide several examples of query execution, and they have several queries as well. And we extract all those queries from that website, and we extract the properties within each query, and we add it into the prompt, and we can get the highest Jacquard similarity average result of 0.7806. So our experiments show that increasing number of properties provided in the prompt result in a higher Jackal similarity score. This improvement is due to the broader range of questions that can be addressed with a wider selection of property candidates. The future improvements include using a more robust state-of-the-art large language model with a larger context window, fine-tuning the large language model with a Sparkle query generation task, and the last one is to integrate additional components. For example, the semantic search pipeline to retrieve relevant properties instead of just passing all the properties into the prompt, which is not scalable at all. Furthermore, we also look forward to compare our systems with other Sparkle query generation systems like ChatKBQA. That's all about our presentation. Thank you for your attention.